Bismillah ar-Rahman ar-Rahim. In this part of the lecture, we are going to see a few examples related to beams. So let's see the first example. And the statement of the problem is that solve the propped cantilever beam subjected to end load P. The beam is assumed to have constant EI and length 2L. It is supported by a roller at mid-length and is built in at the right end. So we have this overhanging beam. On node number 1, we have a point load P acting, and at node number 3, we have a fixed support. Node number 2 has a roller support. Both of uh, these spans are, this overhanging part is L. Similarly, this span is L. So let's see how we can solve this beam. Now, our procedure to solve such problems is the same. That our very first step is to write down the element stiffness matrix. All right. So how many elements are there? We see that we have two elements. We can label this one as element number 1 and this as element number 2. Now first, if we write down the element stiffness matrix for element number 1, it would be something like this. K1 is equal to EI over L cube, and the degrees of freedoms are dy1 phi 1, dy2 phi 2. Similarly, you can label the rows as well. And in this case, we see that the local axis and the global axis are the same because the elements are along the x direction. So we don't need to consider the element stiffness matrix for the arbitrarily oriented element. Rather, in terms of local coordinate axis, we can consider the element stiffness matrix. So that's the 4 by 4 matrix in this form. Similarly, we can write down the element stiffness matrix for element number 2, which is this element, and it's in between node number 2 and node 3. So these degrees of freedom would be dy2 phi 2, d3 by phi 3, and similarly we can label the rows as well. Now, once we have the element stiffness matrices, next step is to assemble them to get the global stiffness matrix. And conceptually, that procedure is exactly the same. Now, in this case, we have a structure which has 3 nodes, and each node has a degree of freedom of 2. So the global degree of freedom of the structure is 6. So the global stiffness matrix would be of the order of 6 by 6. And these degrees of freedom, these columns and rows, they can be labeled as dy1, d1y, phi 1, d2y, phi 2, and d3y, phi 3. Similarly, we can label the rows. And if you look at the degrees of freedom of element number 1, so the element stiffness matrix of element number 1 will take this place in the global stiffness matrix, and by considering the degrees of freedom of element number 2, it will take this place, which is shown by this box in the global stiffness matrix. So this part is overlapping, and here the elements would be added together. So this is the global stiffness matrix in terms in the global coordinate system, or global or local, because we this time the coordinates are the same. Now next is to apply the boundary conditions. So let's see how the boundary conditions are applied. Oh, okay. Basically, after writing down the global stiffness matrix, we have written the force displacement relationship. So these are the forces F1y, M1, F2y, M2, F3y, M3. This is the global stiffness matrix, and these are the degrees of freedom. Now, what are the boundary conditions? D2y, D3y, phi 3, and they are equal to 0. If I go to this figure of the problem. So the vertical displacement is restricted here, and at node number 3, vertical displacement and the rotation are restricted. So we see that the boundary conditions are reported accordingly. D2y, D3y, and phi 3 are 0. So we will delete the corresponding rows and columns. You can write down the degrees of freedom: d1y phi 1, d2y phi 2, d3y, and phi 3. And these the corresponding rows and columns according to the boundary conditions will be cancelled. And once we do that, then we will get this. By applying the boundary condition, the beam equations reduce to this 3 by 3 matrices, right? This stiffness matrix, it is reduced to 3 by 3. And now we can solve the system. At node number 1, we have a force P acting in the downward direction. So that's why we have minus P here. There are no other forces or movements. So this is 0 and this is 0. Now we take this on the other side, take the inverse and we solve it. We get d1y phi 1 and phi 2. Now this time we do not have numerical values in this matrix. So it means that we will not be able to solve it in our regular calculators. So we'll have to do a few mathematical steps in order to find out the inverse of this matrix. Now that's something related to the fundamental knowledge. Those steps are not shown here, but just for your reference, I have done it on a piece of paper, so I'll share that the screenshots of that with you just for your convenience. So you can either mm, just find the procedure online, that how to convert these, how to take the inverse of 3 by 3 matrix in the form of variables, or you can see the screenshots that I will share with you after the class. All right, so when you take the inverse then and solve it, you get d1y phi 1 and phi 2 in this form, pl square over 4 ei minus 7 l over 3 3 and 1. Now if we have these displacements and rotations with us, and we want to find out the nodal forces, then what we have to do, we have to consider the local nodal forces, force displacement relationship. And if we do it for element number 1, the forces and moments are F1y m1, F2y m2, and this is the element stiffness matrix for element number 1, and the corresponding displacements are here. There is a typo in this handout. The first value is correct, minus 7L by 3. The second value, it should be 3. It should be this value for phi 1, which is 3. And similarly, the value for M2, against M2, in front of M2, we should have the value of 1. So just cancel out the 0, this 1 here, and instead of this 1 we will have 3. And then when you multiply these two matrices together, you will get the values of f1 m1 f2y and m2. All right, and the same procedure can be adopted for element number 2. We have the forces and moments f2y m2 f3y m3. This is the stiffness matrix, and these are the corresponding displacements. When we multiply them with each other, we get the force values, force and the moment, 1.5 p pl minus 1.5 p and 0.5 pl. Now we have the element forces and moments, so we can draw these diagrams where these forces and moments are marked on the element. So this is element number 1, this is element number 2, and the forces, if we have just calculated, we have marked them on these elements. For example, for element number 2, the forces and moments are visible here, so we can see that how these are marked. 1.5 p, it's positive, so in the upward direction at this node, and the moment is pl and it's positive. So according to our convention, the nodal forces are positive in the counterclockwise direction. So this is pl, and then this minus 1.5 p, it's acting in the downward direction here, and 0.5 pl. So we have this force, this moment pl by 2. All right, so the forces have been marked, forces and moments have been marked on the elements, and then we can just combine them together to get the forces and moments on the beam as a whole. And you see that At this end, we have force P acting in the downward direction. P plus 3 by 2P, we get 5 by 2P. And these two moments are balancing out each other. So we don't have any uh, moment here. And the force 3P by 2 acting in the downward direction and that moment, those are marked here. Now, once we have these forces and moments with us, then we can draw the shear force diagram and bending moment diagram. That's what we finally want in case of beam analysis. So here you see that the shear force diagram and bending moment diagram have been drawn by the direct method. So force P acting in the downward direction. So we move in the downward direction by an amount of P. Then no force acting in this region, so it remains straight. And this 5 by 2P acting in the upward direction. So from minus P, we go to the positive 3 by 2P, and then it remains linear again. And here we have this reaction acting in the downward direction, 3 by 2P. So we come back in the downward direction. That closes the shear force diagram. And then we can draw the bending moment diagram. At free end, moment is 0, and then we have this negative area minus P into L. So we come to minus P into L, and then this positive area, which is 3 by 2 into 3 by 2P into L. And when we add it into minus PL, we reach PL divided by 2. And here we have PL divided by 2 in the clockwise direction. So that brings the bending moment diagram to 0. So that completes this problem, the first problem. All right, then let's see the next problem, example number 2. So consider a beam shown below. Assume E equal to 30 into 10 raised to the power 6 psi and I equal to 500 inch power 4 are constants throughout the beam. Use 4 elements of equal length to model the beam. So we have this continuous beam which is fixed at both the ends, and we have a roller support at the center. The nodes are 1, 2, 3, 4, and 5, and we can consider the elements as element number 1, 2, 3, and 4. There are two loads acting in the downward direction at node number 2 and at node number 4. Both are equal in magnitude, 10,000 pound acting in the downward direction. Now, this problem is actually like there is conceptually there is no difference in solving this problem. It's we just need to follow the same steps. We'll write down the element stiffness matrices, then we will join them to get the global stiffness matrix. We write down the force displacement relationship. We apply the boundary conditions, and then we get the displacements. And if we need the forces, we can use the local force displacement relationship to get the forces. So I will just quickly go over this problem because there is nothing new in this problem. So let's see how this can be solved. So this matrix is the element stiffness matrix, and there are 4 elements. The numbers are not written here, but this is element number 1, this is 2, this is 3, and this is 4. You may write them down, and each element has the same length, 10 feet. E is same, I is same, so we don't have to write down the element stiffness matrix 4 times. Rather, it is written just once. Ki is equal to Ei over L cube, and diy means if let's say this is element number 1, so it would be d1y phi 1, d2y phi 2. If it's element number 2, then it would be d2y phi 2, d3y phi 3, and so on, right? So we just need to write down the element stiffness matrix once, and once we have this, then we can write down the global stiffness matrix. And how many nodes are there in this problem? For this beam, there are 5 nodes, and each node has a degree of freedom of 2. So it means that the global stiffness matrix will have a degree of freedom of 10. And those are mentioned here: d1y phi 1, this is d2y phi 2, d3y phi 3, d4y phi 4, and d5y phi 5y. And similarly, you can label the rows as well. And if you look at the the degrees of freedom of the elements, then we can easily identify their positions in the global stiffness matrix. This is for element number 1, this is for element number 2, this is element stiffness matrix for element number 3, and this is for element number 4. Overlapping parts are the elements for overlapping parts are added together, and this gives us the global force displacement relationship. Then we apply the boundary conditions. Now, what are the boundary conditions? The boundary conditions at support number 1, we have node number 1, we have fixed support, so d1y, phi1 are 0. At node number 3, we have a roller support, so d3y is 0. At node number 5, we have fixed support, so d5y and phi d5y and phi 5, they are all equal to 0. So we will cancel out the corresponding rows and columns, just uh, like our regular procedure. And once we do that, so how many rows and columns have been cancelled? 1, 2, 3, 4, 5. So originally the matrix was 10 by 10, and we cancelled out 5 rows and 5 columns, and that gives us a 5 by 5 matrix. This is the displacement vector, and this is the force vector. We have two forces acting at node number 2 and node number 4 in the downward direction, having a magnitude of 10,000 pounds. Now we bring it on the other side, we take the inverse, and we calculate d2y, phi 2, phi 3, d4y, and phi 4. So these displacements and rotations will be with us, and once we have them, then we will be able to calculate the corresponding forces and movements. The global forces and movements can be determined. So after the displacements, we plug in these values back to the force displacement relationship, and we get the global forces and the movements, right? And after that, if you want to find out the local forces or the nodal forces, then we can consider the force displacement relationship at the local level, right? Like I'm just quickly going over all of these steps because there is nothing new about these steps. For element number 1, we consider f1y m1, f2y m2. This is the element stiffness matrix, and these are the corresponding displacement and rotation values which we have just calculated. And when we multiply them, we get the local forces and moments. So we do it for element number 1 and element number 2, element number 3, 4. You can just verify these numbers. So this is number crunching, and there is nothing special about that, right? So I just quickly gone over this problem because we there was nothing new in this problem. So this completed problem number 2. Let's see the third problem. The statement of the problem is: consider the beam shown below. Assume E equal to 210 GPa, I equal to 2 into 10 raised to the power minus 4 meter 4 are constant throughout the beam, and the spring constant K equal to 200 kilonewton per meter. Use two beam elements of equal length and one spring element to model the structure. Now this problem is a different problem, right? We have never solved any problem like this in which we had two different types of elements, right? So if we look at this problem, we have three elements in total: element number 1, element number 2, and element number 3. The first two elements are beam elements, and element number 3 is a spring element. So that's something unique about this problem, that here we are going to learn that how to deal with a structure which has two different types of elements. So let's see how that can be done. What are the nodes? Nodes are 1, 2, 3, and 4. Four nodes are there. Three elements are there. Node number 3 is loaded. Load P equal to 50 kilonewton is acting in the downward direction. And these two spans are the member lengths. For element number 1, this is 3, and for element number 2 is also 3. The spring constant is given as 200 kilonewton per meter. So let's see how this problem can be solved. Now, the general procedure still remains the same. We start by writing down the element stiffness matrices, and then we combine them to make the global stiffness matrix, and so on. Just in one step, there will be change, and we'll see uh, how to incorporate that change. So element number 1 and 2, these are beam elements. So we'll take uh, the expression, or the form of element stiffness matrix for a beam element. So you see that uh, for beam element, the element stiffness matrix can be written as this: d1y, phi1, d2y, and phi2. This is the old expression. We are well familiar with this. And similarly, we can write down the element stiffness matrix for element number 2. So there is nothing new about these two matrices. And then we have the spring element. So the spring, for the spring element, the element stiffness matrix can be written like this. Again, we are familiar with this. And spring element is in between node number 3 and 4. So D3y and D4y, and we don't see any rotation here. But now, before we need to perform one additional step before assembling the global stiffness matrix. At this stage, we need to make sure that the degrees of freedom are consistent, because uh, if you look at node number 3, on node number 3, two different types of elements are meeting. On this side, we have a beam element uh, which has displacement as well as rotation, whereas on this side we have a spring element which only has displacement. So in order to adjust the element stiffness matrices so that they are compatible and they can be assembled together, what we will do in the element stiffness matrix of a spring element, we will have to introduce another degree of freedom which is corresponding to phi 3. And we know that there would be no rotation from this side. So the corresponding rows and columns would be 0, right? So on this side, in this matrix, we add here phi 3 corresponding. We add a column and we add a row, but you see that these rows and columns have all zeros. So the objective of adding these rows, this one row and one column, is to uh, make it, make the degrees of freedom consistent. Otherwise, there are no numbers here, so they don't have any effect. The objective is just to make sure that we place these coefficients at the correct position, right? So we have to carry out this step. And one more thing that we have to be careful about is that the coefficient. Here, for the beam element, the coefficient outside of element stiffness matrices are EI over L cube, EI over L cube, whereas we do not have any such coefficient in case of the element stiffness matrix of the spring, right? So we need to make this thing consistent so that we can assemble them together. And for that purpose, what we can do, we can just multiply this matrix with EI over L cube. We can multiply and divide this matrix with EI over L cube, and uh, we'll keep EI over L cube outside, and we'll take L cube over EI inside, right? So that's what is written here. Now, if you see that the entries of this matrix will become K prime minus K prime minus K prime and K prime. And what is K prime? K prime would be KL cube over EI. That will, the K will take this form of K prime when you will place EI over L cube outside of this matrix, right? So instead of uh, the entries being K, these entries will become K prime, and K prime would be this. And that is why you see that the the entries of the spring which are placed here, they do not have k, rather they have k primes. All right. So if we look at the overall assembly of the global stiffness matrix, uh, how much is the global degree of freedom of the system? So we have 7 rows and 7 columns. So basically, the degrees of freedom, the global degree of freedom is 7 by 7. And how these are labeled? The first one is D1 by, then phi 1, D2 by, phi 2, and D3 by, phi 3, and D4 by. Okay, that's how these degrees of freedom are labeled. So you make an empty 7 by 7 matrix. The element stiffness matrix for the first beam, first element comes here. The element stiffness matrix for the second beam, it comes here. And the element stiffness matrix for the for the spring element, it is placed over here. And that's the only trick in this problem, that you have to make the degrees of freedom consistent. After that, you apply the boundary conditions. What are the boundary conditions? If you look at the beam, we have a fixed support here, we have a roller support here, and we have a fixed support here. So you see that the displacement and rotation at node number 1, these two are 0. Displacement at node number 2 and node number 4, that is equal to 0, right? And there is no question about the rotation at node number 4, because there is a spring element, so there is no question of the rotation. So you cancel the corresponding rows and columns from this force displacement relationship, and then you end up with this 3 by 3 matrix. So you take its inverse, you take it on the other side, take its inverse, and then you can calculate the corresponding displacements. So after applying the boundary condition, the global beam equations are reduced to this, right? And then we'll take it on the other side, we calculate the inverse, and we can calculate phi 2 d3y and phi 3. If we do all this manipulation, we get phi 2 d3y and phi 3 as these expressions. All right. And we can substitute the values: length equal to 3 meter, E equal to this, I this, K this, and then we get D3y, phi 2, and phi 3. Always remember that all the rotations will be in terms of radians. And once we have these rotations and displacements with us, we substitute the solution back into the global equations, and we get the corresponding forces and moments as this. And as we have discussed earlier, that the known forces must come out to be same, right? For example, here in this case, the force at node number 3 is acting in the downward direction, equal to 50 kilonewton. So after calculating all the forces, this F3y must come out to be minus 50 kilonewton. If that's not the case, then it means we have made some mistake. So we have all of these global forces and moments. We can apply those forces and moments on the beam, and then we can draw the shear force diagram, bending moment diagram. Those diagrams are not given here, but we know that if we know all the reactions and the applied loading, we can conveniently draw the SFD and BMD. So this completes the solution of this problem.